The traditional method of verifying learning by collecting a final printed paper is obsolete. In an educational environment saturated with generative AI tools, the finished product tells us very little about who actually did the work. Institutions initially reacted to this problem by purchasing AI detection software. Those detectors fail at their primary function. They frequently generate false positives, accusing students of cheating on original work, while simultaneously producing false negatives that allow synthetic text to pass through undetected. Anyone with a basic understanding of prompting can bypass these filters entirely. Simple evasion tactics like asking a model to write with higher perplexity or manually paraphrasing a few key sentences render the software useless. Despite this failure rate, the administrative reflex has been to demand that educators definitively prove a student did not use AI. This places the burden of proof on a negative that cannot be scientifically verified. Because these automated tools cannot reliably prove or disprove human authorship, the current focus on detecting AI-generated text has become an exercise in futility. Establishing academic integrity requires a completely different verification model. To build that model, we have to look at how we define authorship. On this three-tiered framework, the bottom layer is textual authorship. This is the assumption that the person submitting the work personally generated the exact wording and syntax on the page. The middle layer is conceptual authorship. This identifies where the central ideas and frameworks actually originated, regardless of whose fingers typed the paragraphs. The top tier represents intellectual ownership. This is the learner's active ability to explain the logic of a piece of work, evaluate its merits, justify the decisions made, and apply those ideas to a new context. Generative AI fractures this structure. A machine might contribute heavily to the textual production at the bottom, while the human user maintains total conceptual control and intellectual ownership at the top. If we want to assess a student's actual learning, we have to stop trying to catch synthetic text. We have to make the human cognitive process visible and verifiable. The first verification strategy uses the AI itself as the evidence mechanism. By recording the conversational friction between a learner and a generative model, educators can observe the initial doubts, the questioning, and the application of specific disciplinary knowledge. This flowchart outlines the AI thinking conference model. First, the learner establishes their baseline thinking. Second, they use follow-up questions to test the AI's output. Third, they decide what to accept, modify, or reject. Finally, they apply these decisions and reflect on their evolving understanding. The quality of the AI's generation has zero bearing on the student's grade. The assessment evaluates the quality of the student's questioning and their capacity to evaluate the information presented to them. We can see exactly how this works in practice. A recent graduate-level case study tracked a teacher using an AI coach to design a 5-week math unit. The raw materials did not come from the machine. The teacher provided the initial concepts: multiplication, square units, spatial design, and composite shapes, laying out their ideas verbally before instructing the AI to organize them. Midway through the process, the AI failed to correctly distinguish between targeted and enabling knowledge, a crucial technical distinction in the UBD framework. The teacher spotted the error and rejected the response. They pushed back, questioning the AI's logic and forcing the machine to revise its definitions until it matched the framework's rigorous requirements. Later in the dialogue, the AI suggested adding several transdisciplinary ideas to the curriculum. The teacher rejected this advice entirely, determining that a 5-week unit was already conceptually demanding enough for the students. The strongest evidence of learning in this case study is the documented friction, the professional judgment required to recognize bad advice, push back on inaccuracies, and steer the project back on course. The second strategy scales this visibility into an institutional requirement, replacing the black box of final submissions with an auditable paper trail. Universities like Tampere in Finland now require students to save and submit their entire chat histories and prompt logs alongside their assignments. This creates a transparent, chronological map of how the ideas were constructed. Evaluators review the intermediate steps, the rough brainstorming notes, the structural outlines, and the messy early drafts, verifying the human effort that took place before the final polish. When AI is used to assist in the final output, institutions mandate formal written disclosure statements. These disclosures require students to explicitly itemize the division of labor. The student must document exactly which tools were used, how they were utilized, and the extent of the machine's influence versus their original contributions. Verifying intellectual ownership does not require forcing a student to work with zero AI assistance. It requires absolute honesty and documented transparency regarding where the human hand ends and the automation begins. When digital paper trails are insufficient or a student's ownership of a project is actively questioned, educators fall back on the third strategy, oral and practical verification. The student must be able to sit down in person and verbally deconstruct their own work. They have to articulate the specific logic, the sourcing decisions, and the analytical processes that led to their conclusions. By asking spontaneous questions about the material, the evaluator verifies that the student's real-time mastery of the subject is consistent with the depth and tone of the submitted document. If inconsistencies remain, the ultimate proof of authorship is a controlled re-demonstration. The student completes a similar task or writes on the same topic in a supervised environment, proving they possess the skills demonstrated in the final project. The fourth strategy bypasses the text generation problem entirely by shifting the format of the assignment itself. Instead of assigning isolated essays, educators are implementing social and collaborative annotation tasks. Students use platforms to publicly annotate assigned reading material, leaving notes, critiques, and questions in the margins for their peers to see. This forces the critical analysis out into the open, making their active engagement visible to the instructor in real time. Collaborative tasks transform verification into an organic, observable part of the daily learning journey, rather than a forensic audit performed after the work is submitted. A polished document sitting in isolation on an instructor's desk can no longer serve as proof of independent thought. To verify learning, we string these strategies into an evidence system timeline, starting with initial thinking, moving into AI dialogue, analyzing critical questioning, and evaluating independent decisions. We then track how decisions drive revision, shape the final artifact, and culminate in a self-reflection. This framework scales across education levels. While a graduate student will exhibit more complex professional judgment than a primary school student, the core criteria, evaluating what the human brings to the exchange, remains identical. The focus of the assessment stays entirely locked on the learner's independent contribution to the dialogue, measuring their ability to guide the tool rather than simply consume its output. The productive focus for educators is the intellectual work the learner contributes to the human-AI partnership, rather than the binary question of whether a machine was involved in the text generation. By utilizing AI to make thinking visible, institutions secure academic integrity through transparency, effectively ending the assessment surveillance state.